By the end of this topic, you will be able to identify the relationship between a numerical target variable and a categorical variable using Anova. Now, let's talk a little bit about Anova. Anova stands for Analysis of Variance, which checks if the means, that is, average value of the target variable across different levels or unique values of a categorical variable are equal or not. It assesses the importance of one or more levels by comparing the means of the target variable at different levels of the categorical variable. So basically, in our example of condition of house versus sale price, it looks at the average sale price across different house conditions and concludes if the average values are statistically different or not. Now, when we execute Anova, we have certain hypotheses: the null hypothesis and the alternate hypothesis. The null hypothesis states that there is no difference in means, while the alternate hypothesis states that at least one of the means is different. Now you may be wondering if we can already see it from the graphs that average sale price across different house conditions is indeed different, then why do we need Anova to establish the same? That is because often you may get difference in means purely by chance, and that may not be the true representation of reality. Now let's say you want to find out if the average height of people in your locality differs from that in your friend's locality. Both of you take two random people from each locality, measure their heights, take an average and compare. Now say your average comes out to be 5 feet 2 inches, while your friend's average comes out to be 6 feet 1 inch. Based on this alone, we can conclude that average height in both the localities is different. No, because it is quite possible that by chance the two people you met in your locality were shorter people, while your friend happened to meet taller people, and hence you see a difference. Had you taken larger samples, or say measured everyone's height, you may have found that the averages are quite close to each other. Anova helps us answer this important question, that if we are observing difference in mean value across multiple groups, how likely it is that this difference could have occurred purely by chance, and hence these groups cannot be counted as different from each other. This can also be examined based on two values that we get when we perform Anova. One is f value, which should be a large value, and the other is p value, which should be less than 0.05 if we wish to reject the null hypothesis. That is, the means are same, and accept the alternate hypothesis that means are different and the categorical variable does have an impact on target variable. A p-value of less than 0.05 means that there is less than 5% probability that the difference in means that we are observing could be purely a coincidence, and we are 95% or more confident that the difference in means actually exists. There are two types of Anova, that is, one-way and two-way. When we deal with one independent variable, we do one-way Anova, and when we deal with more than one independent variables, we do two-way Anova. Here, since we are looking at the variance in means of target variable across different levels of one categorical variable, we would use one-way Anova. Now, if you want to know more about Anova, please go through the link given in the helper text. We have understood what one-way Anova is and how does it help us in data exploration. Now let's see how we run one-way Anova, and for that we will be using two libraries. So let's import them. Now there is a simple modification that we have to do with the variable names. Otherwise, Python won't be able to understand the codes and give us error. In Python, we generally use variable names with no spaces in between. Like for example, sale price, it has a space in between, and if we use the code as it is, the system will give us an error. So to overcome this error, we rename the variable name to sale_price and the blank would be removed using the rename function. So let's write the code for removing the blanks. We have renamed the variable. Let's check how does the data view looks like. Now let's write the code for renaming the other three categorical variables which we will be using in our analysis. Now let's run Anova for sale price and condition of the house. For that we use the function OLS and fit the model. Next we create the one-way Anova table using the stats library. And the final step, let us check the final table or the summary table. So from the output we have the sum of squares, degrees of freedom, F value and P value. The F value is 58, which is high, and P values is less than 0.05. And hence, we reject the null hypothesis and accept the alternate hypothesis that there is difference in means. Now as we had discussed earlier, Anova can tell us if a variable has an impact on other or not. But it can't tell how strong or weak the impact. Let's write the code for the other three categorical variables and see the results. We see that in all the three cases, the p-value is less than 0.05 and hence we reject the null hypothesis and accept the alternate hypothesis that there is a statistically significant difference in means, and hence these categorical variables do seem to have impact on the target variable and should be included in our model. So that concludes our discussion on relationship between a categorical and a numerical variable. We will assume our discussion on exploring categorical variables in the next tutorial.